To begin our discussion on dynamical systems, we're going to start with linear systems of autonomous differential equations. In the past video, we talked about this as being the governing dynamical equation. It is a system. In particular, we're going to take a look at having only two states, so a system of only two differential equations that are coupled together. And the reason for that is because it's easy to visualize what's going on, but the idea is definitely generalized to higher dimensions. And so what we're going to show is that the behavior of these is dictated entirely by the properties, in particular the eigenvalues, eigenvectors of this matrix A. So if you do your eigenvector, eigenvalue decomposition, to find your eigenvalues, the first thing you do is you try to find where the determinant of A minus lambda I is equal to 0. That's going to give you a polynomial in lambda, and you're going to solve for where lambda is equal to 0. Solve where that characteristic equation is equal to 0. And those values of lambda, if you solve out, looks generally like this. It's a little nasty just because we're keeping it very general, and P and Q represent the trace and determinant of A. But kind of stepping back from that complicated equation, it's easy to see that you've got options where the eigenvalues can be complex. So remember, complex happens when this discriminant here is negative. That means that that's going to become a complex value. Complex values always come in conjugates, which means they come in pairs, where A is the real part and B is the imaginary part. That complex conjugate means that we have this plus or minus. If this discriminant is not negative, then that means that you're going to have real eigenvalues. And so you could either have both of them being positive, both being negative, or they could have one positive, one negative. The case where P squared is equal to 4Q, the discriminant is equal to 0, that's where you have two real values that are exactly the same value. And that's a little bit of a degenerate case. So for now, what we're going to do, we're going to be talking about linear systems that don't have eigenvalues with 0 real part. And that's going to help us say that there is exactly only one equilibrium, because this is getting a little deep in linear algebra, but then there's no vector here that could be in the null space of A to generate x dot is equal to 0. So equilibrium is defined by x dot being equal to 0, and if there are no eigenvalues with 0 real part, then that means that there are no values other than x is equal to 0 that make x dot equal to 0. And so that's going to be critical, and that's going to be our equilibrium, and the shape of the dynamics is going to be plotted with respect to the states x1 and x2 as you move away from that equilibrium. The first thing we want to do to help quantifiably describe the evolution of the differential equation is to understand what the solution looks like. And so this parallels what solutions look like for linear differential equations of a single variable. So now that x is actually a vector, what we're going to do, and it's described by this differential equation, if lambda is the eigenvalue and v is the eigenvector, we can guess this as a solution. And what we do is, if we take the derivative of this guess with respect to time, that's what this derivative is, then this pulls this lambda down in front, and then we get the same thing back again, because v is not a function of time. And then we get a multiplied by e to the lambda t. And this equation, we want to be able to satisfy this equation for all time. And so that means that we can actually cancel out these exponential terms, and you're just left with lambda v av. And so it shows you that indeed it is the eigenvalue and eigenvector then that characterize the solution of this differential equation. Now this could be one of the eigenvalue eigenvector pairs, but it actually will hold for all of them. And so our solution is not just one of them, but it's actually in general, it's going to be a sum of all of the different combinations, essentially linear combinations, because we've got these different coefficients out front. And so essentially different amounts of each of these modes, where e to the lambda 1t represents the eigenvalue contribution and in the direction of V1. And so you're going to add up all of these contributions, and so the solution will generally be written like this. And so we've seen something that looks vaguely like this from diffusion, and even back a little bit further if we think about the eigenvector discussion earlier in the course. So we have many different types of what are called phase portraits. And so the first and probably the simplest, one of the simplest, is the saddle. And so remember, if we have two states, then our differential equation is in general going to look like this. And so these eigenvectors are going to be important, as are these eigenvalues. And so a saddle happens when you have one of your eigenvalues being negative and one of them being positive. So arbitrarily, we've picked this one as lambda 1 being less than 0. And so what that means is that when you put lambda 1 and it's less than 0 up here, that means this exponential term is decaying. And so we expect that the motion, the state trajectory along the V1 direction to be diminishing as time goes on. And so it's exactly what's happening if you look at the motion of this system along this way. The way that we're plotting this here, the figure that I stole here uses x and y, but we can think about these as being x1 and being x2, which is what I've been using in the previous slides. So this is a phase portrait, and it tells you in terms of the two states, x1 and x2, it plots the trajectory. And so it means as time moves on, that's what the arrow is implying, that we move like this along this streamline. And so if we're looking at the projection along this V1 direction, which is given by this black arrow, then you see that the amount of the solution x that is in this direction gets smaller and smaller. So when it's here, the projection is here. When it's here, there's this much. When it's over here, there's this much. And so it's asymptotically approaching the origin. And that's exactly what we see from this exponential term. From the opposite point of view, we can think about in the direction of V2, that's along this black line, this arrow, that the exponential term here, if lambda 2 is positive, then that means that this exponential term is growing. And so we see that initially this is here, and then it moves out, and it grows exponentially, and you can see it'll just keep growing. And so this is one of our important types of phase portraits. It's called a saddle, and so you can. What's helpful here is to be able to separate, and this is because it's linear, we can separate and then add together the two contributions of these two pieces. And again, if you had higher dimensions, you'd still be able to do that. The second type is a node. So if our lambda 1 and lambda 2 are not the same, and either they are positive or if they're negative, we get these two types. And so we haven't really talked about stability yet and unstable, but the kind of as a kind of gut feeling, stable means that things are approaching the origin and they're staying contained and they're not blowing up. Whereas in the unstable node, you see trajectories that are leaving and growing and getting bigger and bigger, just like in the saddle. There was a direction which the state trajectories were just getting bigger and bigger. So stable and unstable, these correspond to whether the exponents are negative or positive. So just like before, if both x1 and x2 are negative, just like this is saying, then that means that along both directions, the trajectory is going in to the origin. And so we see that in these streamlines, that these go and they approach the origin. When the exponents are both positive, that means that no matter where you start, you then exponentially increase. And so in this case, we've chosen, these diagrams are particular such that lambda 2 is faster, it's bigger value than lambda 1. And so that's why you see, in this case, along V2, things happen faster. So from here to here, X2, or the state along V2 has changed this much, whereas along V1 has only changed this much. And so that's how you can tell which of the eigenvalues is larger. A degenerate version of the node phase portraits is when these two eigenvalues are actually the same value. Again, this is where the discriminant is equal to 0. And so here you can get a variety of different types of behaviors. So again, if we have positive eigenvalues, you're going to get unstable type trajectories. If you have negative eigenvalues, you get stable trajectories. But the difference between the upper plots and the lower plots is something more theoretical, and it has to do with the eigenvectors of the matrix A. And so either you'll get this type of star, either stable or unstable star, or you'll get this type of graph or phase portrait. And so we'll talk about just a little bit about why you might get that. So we said that the solution looks something like this. And so we also had a little footnote there that said that this is the usual case, but it can get a little trickier. And so we can leverage this theorem, which says that if we have all distinct eigenvalues, that we will definitely have all linearly independent eigenvectors. However, kind of the corollary to that is that if we have a repeated eigenvalue, so some value that gets repeated multiple times, if we have n eigenvalues, we have anywhere from 1 repeat to n repeats. And so there are two options. So the number of repeats is essentially called the algebraic multiplicity. And you can either have geometric multiplicity that is equal to algebraic multiplicity or not. And so if these two things are equal, then this still holds. And so what is geometric multiplicity? Geometric multiplicity is the number of linearly independent eigenvectors. And so if it has the same number of linearly independent eigenvectors as algebraic multiplicity, essentially as many times as the eigenvalue is repeated, we have that many linearly independent eigenvectors associated with that eigenvalue, then your system looks just like this. Your solution looks just like this, just as what we said. However, if you're deficient and the geometric multiplicity does not reach the algebraic multiplicity, what ends up happening is that you have to generate certain generalized eigenvectors. And this kind of gets beyond the scope of the course, but the idea is to see that we now change the general solution. So for the one eigenvector that we do have, that we can find associated with lambda I, we get this term. And for one where we don't have the other eigenvector, we get this generalized eigenvector, and what ends up happening is there's this t term, and that's what gives rise to that kind of slanted shape that you saw on the previous slide. Now that we've dealt with the real value cases of the eigenvalues, we'll talk about the complex conjugates. So if we have a complex conjugate, the eigenvalues look like this. Again, A is the real part, and alpha is the real part, and beta is the imaginary part. So if the general solution looks something like this, then that means that the lambda will be up here in this exponent, and we can use our exponential rules to pull out the part that corresponds to the real part of that eigenvalue. So that's e to the alpha t. And then the rest of it is going to be rewritten in terms of the Euler formula, which remember e I theta is equal to cosine theta plus I sine theta. And so using that Euler's formula, we can rewrite this in terms of cosines and sines. In general, the eigenvector is also going to be complex, and so it means that there's going to be a real part and imaginary part of that vector. So one of the tricky things, and not so obvious until you kind of look through it and solve it, is the fact that if you take the real value of this expression and the imaginary value, those are actually independent solutions. And so that involves, one of the ways of seeing that is that you essentially have to separate these different pieces, the imaginary parts, out from everything else. One important thing to appreciate, though, is that this alpha value is what determines the stability, whether trajectories essentially go towards the origin or away from the origin. And so, because this is something that oscillates, and this is something that either grows or decays. And so if alpha is positive, that's going to grow. If alpha is negative, that's going to decay. Again, we talked about not considering cases where the real part is equal to 0, but it's worth kind of taking a look just to see what they look like. And what ends up happening is that means that e to the alpha t out front just becomes 1 because alpha is 0. And what that means is that there's no growth or decay. It's simply just all of these circles or ellipses. And so this is an example of marginal stability where the trajectories aren't necessarily growing or diminishing. But it makes it difficult to say something about this because when we talk about stability, because it doesn't have a unique equilibrium. And so this slide simply just shows you a little bit of a decomposition of, in terms of the trace of A and the determinant of A, all the different possibilities, and understanding that this is the discriminant here, that essentially everything stable happens over here in this part of the graph, and complex values happen inside the discriminant, and real values happen outside.